Our next presentation is by Dr. Ahmed Jamil, CTO of EcoTechX in the United Kingdom. Dr. Jamil works on cooling system, refrigeration, and solar-based water production with multiple awards and major funded innovations. Today, he will present solar to water, a novel solution for water neutral communities. Dr. Jamil, go ahead.
Hello, good afternoon, everyone. So can you see my screen?
Yes.
Okay, thank you very much. And I hope you can hear me clearly as well. So thank you very much for inviting for this presentation today. And today I will be presenting about one of our novel system that's hybrid solar to water system. And we have developments from material and process perspectives. Uh, I'm Dr. Mohammed Ahmed. I am currently working as Chief Technology Officer at EcoTechX and Senior Research Fellow at Northumbria University. So here is the system that we have developed, and definitely I will be sharing the whole journey that how we were able to get the system to this level where we are actually testing it. So just a bit of the background, if we look at the sustainable development goals critically and we will come up with the idea that we can relate them with three of the major goals that are related to water. For example, the sixth one, which is clean water and sanitation, affordable and clean energy, and climate action. So all these three are directly or indirectly somehow related to the remaining 17 one, and these are directly associated with the air water generation mechanism or air water harvesting. So these are the three that we are currently addressing through our system and engineering developments. So about the water supply demand gap, I will not definitely go into details as most of us are water expert. And in the nutshell, we are suffering this water supply demand gap. And this gap currently is fulfilled majorly by desalination technologies. However, a minute contribution from other strategies like unconventional sources and improved water utilization are covered, but majorly more than 90% is covered through the desalination system. And when we look into the desalination systems, we can categorize them in different in different categories from different perspectives. For example, they can be from the thermal side, membrane side, or other unconventional methods. Meanwhile, we can also categorize them based on their size. For example, on city level, if we need, we will be having bigger systems like multi-stage flashing, multi-effect desalination, vapor compression systems, or reverse osmosis. But on the town levels, we can have membrane distillations, electrodialysis. Meanwhile, we are more concerned about the decentralized solutions where we are dealing with the house level systems or the house level problem solution. And there we come with the solar stills and air water generators. When we go for the solar stills, they are very passive devices, and getting the required amount of water is sometimes really hard in these systems. The other option that is an excellent alternative to this solar stills is air water generator, where we don't need a big infrastructure. Rather, these systems use the humidity in the air and produce clean drinking water. And this is the sector where we are currently working on. If we explore the air water generators or air water harvesting systems, we come up with three major categories. One is desiccant based systems, another one is condensation based dehumidifiers, and the third one is unconventional systems like dew collection, fog harvesting, etc. But majorly in the market, these two exist, and among these two, the systems majorly used for drinking water purposes are desiccant based systems. So we have done a critical review of different patents since 1900 to 2020 to understand that how the developments have been done over the years in this air water harvesting systems. And we come up with the conclusion that desiccant based air water generators are the most commonly used and the one of the robust techniques to produce water for decentralized applications, particularly remote locations like field hospitals, army camps, etc. So that's why we chose this site to conduct our research and development to improve the performance. So if we look at the desiccant-based air water generators, there are certain properties on the material level that are required. For example, we need adsorption enthalpy, a certain pore volume, crystal size. So these are the parameters that affect the adsorption system performance. Similarly, some other parameters like packing porosity, thermal conductivity, heat losses, etc. So and these are the material level things that we have to work on to get the maximum efficiency or the performance. But if we look on the system level, we can summarize these in four major things. The very first thing is low energy demand. Definitely, if we have to come up with a system that can fulfill the requirements efficiently, we should have lower energy consumption. Similarly, high water uptake so that we can have a decent size system for the water production. If the water uptake is very low, then definitely we have to go for very high area footprints. Cyclic stability, because these air water generators go under adsorbent, desorbent, desorption phases. So during these cycles, their chemical composition or their mechanical properties are basically what you say are mitigated during the process. So we are looking for the system that are very stable and give the very good cyclic stability. And lastly, very fast capture and release so that we can produce water in a continuous manner rather than going with the large intermittent times. So these were the characteristics that we have focused in our system while development. So just going into the typical operation, these systems work during the night time. They go under adsorption process because during the night time we don't have solar energy available, so air keeps passing through these desiccant wheels, and these are being saturated. But during the daytime, when we have solar energy available, we can use this heating mechanism to regenerate these systems and produce water for the for drinking purposes. So in these systems, we have two major limitations. The one is material and heat transfer mechanism for regeneration. And secondly, the passive operation, because we have to wait for the renewable energy to maximize the performance, or even these systems operate in some of the areas where we don't have the grid operations. Rather, we have to rely on the solar energy. So in desiccant-based air water generators, different adsorbents are used, and for example, graphenes, maxenes, and MOFs. But if we look critically into the actually developed system, we will come up with the conclusion that silica gel is one of the most commonly used. There can be different reasons. For example, this it's abundantly available. Secondly, the cost is very economical. Though some other materials give very good performance compared to the silica gel, but definitely when we talk about the system level development, we have to go for the option that is technically viable and economically feasible for the large scale system development. But if we look at the conventional silica gel based systems where the beads are packed in the heat exchanger, they have certain limitation because of this arrangement. For example, the beads will come up with the point contact area, which is a very small area, so that's why the heat transfer will be very poor. Similarly, high mass to area ratio, they required a lot of material to be packed in these heat exchangers to come up with the required performance. So because of these reasons, they are prone to 6 or 7 different type of heat transfer resistances within these heat exchangers. So because of this reason, generally the thermal contact resistance represent around 25% the overall heat transfer resistance. So that's why they have very poor heat transfer performance. And if we have to come up with the high performance of the overall system, we need to look into this mechanism, and this is where we are contributing, and we come up with a novel idea. So basically, we are replacing these beads-based silica gels and directly coating powdered silica gel on the heat exchanger surface. So one of the biggest challenges was to identify the required binders. So we studied different binders that can hold that powder on the surface of the heat exchanger without leaching out during the process, because the cyclic stability is one of the key challenges and one of the key requirements of the system to operate on the robustly on the industrial scale or on the large scale. So we have tested different binders, but we come up with the conclusion through extensive experimentation that hydroxyethyl cellulose is one of the best organic type binder that can be used for this purpose, and we use this one to coat our powdered silica gel on the heat exchanger plates. So if we compare just quickly one on one with the type 3A and type RD powder, the powder one we are using, we can get a very good particle size, which is very small. That's why it will have high contact area with the surface. Similarly, the surface area it offers is quite good, meter square per gram, and porous volume, specific heat capacity. Meanwhile, the binder is also giving us very good properties that that can achieve a good performance compared to the beads based silica gel. So we did some experimental testing by coating this powdered based silica gel on the heat exchanger, where you can see at the basically the resistance in the heat exchanger was significantly reduced. So these are the results for the HEC based binder powdered silica gel on the heat exchanger, and these are the conventional bead based silica gel systems. So you can see we have significantly reduced the heat transfer resistance within the system, that can boost the performance and reduce the size. So because of that reason, we got a very good high overall heat transfer coefficient that speeds up the process for this regeneration process for our system, that is HEC based the base system that we developed using the powdered silica gel. So from these extensive experimentation, we come up with the conclusion that temperature differential reduced from 17 to 5 degrees C, which boosts basically the heat transfer process. So because of this reason, we are getting very high overall heat transfer coefficient from 40 to around 120. With the coating of this particles of the silica gel using this HEC binder. So because of this reason, we are getting two benefits. One is we are reducing the size of the system, and secondly, we are getting very good heat transfer mechanism. So that's why the cyclic the time is very short compared to the conventional systems. So here is that cyclic performance, experimental cyclic performance is presented. You can see that in the conventional packed heat exchangers, we need 800 second time to switching, and 45 seconds as switching time before going into the generation and regeneration process. But when we come up with this powdered based silica gel, this time is significantly reduced to 200 seconds. So that's why we can have multiple cycles of this adsorption desorption during this process. So that's why we are the system that we have proposed produce more water within the same time, and meanwhile by offering high heat transfer efficiency and better heat transfer coefficient, that also reduce the size. So we got some of the conclusion. For example, it reduced switching time due to less heat transfer resistance, low thermal and convective resistances, high heat transfer rate, cycle operation is faster than the conventional packed bed heat exchangers, and it can reduce unit size for the same capacity, which was one of the major concern because it's a passive device. So the area footprint is very important when we are talking about liters of water production per day. And similarly, the performance can be increased for the same size. If we are taking the same area footprint, we are getting more water production. The second thing that we are working on is the active regeneration through microwave, because in the conventional systems, we have to heat up the whole wheel section by section to regenerate it. So that's why it takes a lot of time and a lot of energy to heat up that section. So rather than going using the conventional heaters, we tested this microwave based magnetron heads that can directly hit the water particles on the silica gel heat exchanger. So that's why it will offer a targeted operation, and it will excite water molecules, heat up them, and then it can dissolve very fast the heat exchanger that we are using. So because of this reason, as you can see here, initially we were having very low humidity, but as soon as we turned on our microwave based process, the humidity goes up very fastly. So it shows that this process can be the regeneration process can be achieved using this microwave based technique very fast and very energy efficiently by directly targeting the water molecules rather than striking the silica gel beads and getting just the a little portion of water out of it. So this is the second process that we have integrated with our system. So based on these two integration in one system compared to the conventional systems where they have packed the silica gel beads and used the conventional heaters, we come up with a relatively high COP, that is 0.58, which signifies the importance of the system that we developed. When we compare it with the conventional COPs that are less than 0.5, 0.4, zero point 0.3, so the system can offer several benefits from energy viewpoint, from area footprint viewpoint, and similarly from the cost viewpoint. So we have developed this system on the on TRL level 6, and this you can see here, and we are testing this system at Northumbria University in UK at different humidity conditions. And definitely we are also working on decoupling the system from the external air humidity through further innovations where we can minimize the effect of outdoor air humidity on the overall stable system performance. So based on this concept, we received 300K seed fund from Innovate UK, and we developed this system from lab scale to the actual operational scale system that is operating on the solar energy currently for 24 hours in the university. So we have pitched this idea to several academic and business people or experts, and we have received several awards and some of the early adopter orders for the unit to test. And currently, one of our system is being tested in Malawi in South Africa because the conditions are drastically changed from UK. So that's why we are also working on maximizing the water production of these systems in those arid areas like Africa or Pakistan, India, where the temperatures are very high and the conditions are very dry in certain weather conditions. So overall, from the system viewpoint, we have worked on the heat transfer improvement by employing the powdered silica gel and identifying the best binder for this to improve the cyclic stability of the system. And we have also improved the energy performance of the system by incorporating the active regeneration that can break the limit of this intermittent water supply rather than going into the continuous water supply for these systems with solar energy. So thank you very much. This is all from my side from the technical development that we have been doing.
Okay, thank you very much. Everyone, if you have any question, please just raise your hand. I will unmute you, or you can write it in QA or in chat section. We already have 2 questions from you. Okay, I want to ask you about the potential absorption desalination technology, and I want to know your opinion about scaling up absorption desalination. Is it feasible in your opinion, and why?
From the desalination viewpoint, definitely absorption desalination techniques have been used, but the main idea for air water generation based on the absorption based chiller absorption based systems is to go for the remote areas where we are not looking for a big infrastructure to implement. And many of the areas are where even the saline water is not available. So you have to rely on the decentralized solution. So desalination can only work in the areas where we have the salty water available, and then we can look up for the different techniques to work on, like adsorption desalination, multi-effect desalination, etc. But in the areas where we don't have anything like that, we have to rely on the air water, so that then this adsorption based air water harvesting systems are preferred because we don't want to play with the infrastructure, particularly in the remote areas.
Thank you. Ibrahim, you can right now unmute and ask your question.
Yeah, my question is the first, you mentioned about the energy consumption, you reduce it with the use microwave for heating. But my question, how much energy you consume to produce 1 liter of water? That's the first question. The second one, you mentioned that coating is much better than packing, which shows low thermal resistance. But in terms of footprint, because with the system footprint, you're going to use less material than packing. So how this can improve the footprint with using much less material?
Yeah. So let's answer the second question first, because we are using the plates first to coat and then develop heat exchanger from that. So that's why we are getting perfect coating on the heat exchanger, where we can increase the area contact area with the surface. Because in the beads, since it's a single point contact, so overall bead has a very small amount of point contact that will reduce the heat transfer by increasing the resistance between the two surfaces. So this is how we are getting better heat transfer and compact area. The second thing you talked about, the energy consumption. I'm not very sure in terms of numbers that how much we reduced, but we come up with the final conclusions of the payback period of the system, and it's within 6 months for the current system. While if we compare it with the conventional systems and using the same beads based silica gel and the conventional heaters, that is over 1 year. So in terms of cost, we are offering much better efficiency and economic viability of the system.
Yeah, but then how much energy then consumed to produce 1 liter of water?
I'm not very sure about the number currently with me, but definitely we have calculated it at certain stage.
Okay, we have some also
Okay, thank you.
questions in the chat. What is water production of this system at 30, 60, or 95 humidity in liter per kilogram of material per day?
Yeah, so definitely it's a modular system and we can develop a system of different capacities. Currently, the system that I have showed is 15 to 20 liters per day, depending on the outdoor air humidity. But we are working on improving this direct impact of the outdoor air humidity on the system by incorporating another novel system. Definitely, we are working on that. That will further reduce the dependency on the outdoor air humidity. So currently, the system that I showed is 15 to 20 liters per day, depending on the outdoor air humidity, varying between 40 to 60% or 70%.
Awesome. And another question from Ramesh. What's energy
Yeah.
efficiency kilowatt hour per liter at certain ambient parameters?
So regarding the number of the energy consumption, I don't remember the exact value, so that's why I will not quote any misguiding value. But we are more relying on the payback period of the system overall from energy and economic viewpoint. So which is less than 6 months as compared to the conventional systems. But the next question is, what's the lowest RH? It can work as the conventional system can work to the lowest RH, like 30-40% even. But still, as I mentioned, we are also working on the innovating that side of the system currently to decouple it from the conventional from the outdoor air humidity by adding few more components that can improve the stability of the production, watt production.
Yes, Professor Paul.
Yeah. Hey, Mohammed. Thank you. That was a really nice presentation. There's lots of cool science in there. I guess I was also super impressed that you were able to kind of get to the point that you are with this prototype for, what was it, 300,000 pounds? Is that what the total investment is to date, or is that what you have for the next step? Could you tell us a little bit about, yes, you won prizes. Congratulations.
Yes.
But how much money do you need to go the next step?
Yes. So this 300K was actually the seed fund to develop from lab scale to the actual pilot scale system that we tested, and we got some attractive results. So in our next stage, we are going for two directions. Definitely, the one is from the investment viewpoint, where we are trying to raise some money to develop this system and test it in different areas where there is no water, particularly war-torn areas or African places, schools, by contacting with NGOs, and we do have some early adopters from that point of view. And we have delivered some systems to them, and we are looking for around 300 to 400K invest in terms of investment. Second stream that we are exploring is further R&D in this system. As I mentioned earlier, that by to reduce the dependency of the system to the outdoor air humidity direct impact, we are trying to break down this limit so that these systems can operate at lower humidities as well, by retrofitting some more components, and we are working on that side. So from that viewpoint, we are working on the research proposals to EPSRC and Innovate UK to get some more funding and do some experimentation on the lab scale first, and then implement on the system level. So currently, from the business viewpoint, we are looking around 300 to 400K more to develop these systems and deploy on sites.
That was very interesting. Thank you, Dr.
Thank you.
Muhammad. Okay, our next presenter. We now welcome Dr. Anique Azam, Assistant Professor at NED University of Engineering and Technology. Dr. Azam has been active in atmospheric water harvesting research since 2018 and has supervised many student projects in AWH development. His talk today is on indicators for performance of MUF-based AWH system. Dr. Azam?
Hello and good evening, good morning to everyone, because we are an audience from around the globe. My name is Anique Azam, and I'm currently serving as an assistant professor at the ADD University of Engineering and Technology, Karachi. I also happen to be a member of the International Water Association and serve as a member of its strategic council. While I've also been a part of the IWA Green Force Youth Action for SDG 6 Fellowship. The topic of my presentation today is about the indicators of the MOF-based atmospheric water generators. It very nicely complements the presentation that have been given so far, starting from Dr. Lucia and all the way to Dr. Ahmed, and the question that was posed by Dr. Paul about the systems approach. The motivation, I believe, is very similar for every one of us who is working in this field. The purpose to add the slide over here is that the atmospheric water harvesting is no more technology for the developed world only. Rather, the global south is also really trying to catch up with the unconventional sources of water because of the disproportionate effect of the climate changes that is being faced. I have tried to slash my presentation down. This is a part of my doctoral research, and I'm presenting in this presentation a very brief overview of the pinnacle of that whole research that was carried out. Being a mechanical engineer, it is slightly sometimes difficult for us to get our heads around the chemistry of the adsorbents that we are using, and with new adsorbents coming every other day in the market, how are we really going to understand which adsorbent is going to be fulfilling the requirement or the unique requirement of every region around the globe, and let alone the techno-economic feasibility for the global south? We really need to come onto a KPI, which is going to guide us to material that we can foresee to be fruitful in the field. This slide is a standard, simple psychrometric chart. The process that we are going to be looking at will be the passive atmospheric water harvesting mechanisms. And specifically because MOFs are a new field, are a new material, so we have tried to produce KPI for MOFs, but that does not limit it to only MOFs. Rather, they can be applied to other desiccants of choice as well. When we start looking at the indicators in the literature, one big gap that we find is the group of the researchers who are making materials. They are often very much devoted to a larger value of the water uptake. They're also very much inclined to report the kinetics. But when we see that the materials, when we bring them to field, we are dealing with engineers who are in planning and estimation, who have come from backgrounds where things had a certain value of efficiency. They had a top ceiling, which gave them a realistic understanding of how certain systems are going to work. The majorly reported indicators in the order of precedence when we studied about atmospheric water harvesting were water generation rate. At first, a lot of papers, I've shown a pie chart of that 45% of the papers, which were original research articles that were studied, talked about water generation rate as an indicator, as the sole indicator for the atmospheric water harvesting system. The next one, very important one, the specific energy consumption of water amounted to 21% of the total pool. And then the water generation rate per area, specifically when we talk about the newer methods such as the radiative cooling as presented by Dr. Ali, and some other strategies which deals with the spreading out desiccants to very thin layers and hydrogels. And then some papers, approximately less than 10%, started talking about efficiencies and then COPs, which really makes me think that the legacy indicators such as COP and efficiency, are they really not being good? Are they really not proving good enough to go to the next level where the materials are being made and we are not able to use them? We then try to develop a comparative table where it was seen that the indicators which are very commonly being used to report the effectiveness of the atmospheric water system, or predominantly the materials that are being made for atmospheric water harvesting, they do not really have defined limits. The sky is the limit for them to go. Um, uh, so it will become slightly difficult for the designers of the system to understand whether they need to invest a good amount of money in having or incorporating MOFs, or if they can get the um, same level of output and same level of effectiveness from using the good old silica gel. The scientific gap was basically the need of indicators which are customized for passive water harvesting systems, and they should be robust to the current growth of the adsorbent research. It might be true that some other adsorbent is discovered in the next 1 year, and that becomes the highest benchmark, that becomes the ceiling. But what can be a theoretical ceiling for any adsorbent that is to come, so that the designers of the system can exploit the use of those materials in the best possible manner. So this part was divided into 3 simple steps. The first step was to simplify the model of adsorption. The model that I proposed is inspired from the lattice model of adsorption, where certain assumptions have been taken to simplify the development of the indicators in order to achieve an ideal, or in order to achieve a ceiling value for the indicators, so that any realistic adsorbent would fall below that particular value. What we can see in the slide is the general adsorption behavior of any adsorbent material. The first assumption that is being taken to make the indicators is that the adsorption is only happening on the projected area, and the lens on the sides of that adsorbent material, they particularly are not participating in the adsorption. So this reduces the adsorption phenomenon to a one-dimensional phenomena. As the time proceeds and adsorption starts, we can practically feel that the water content inside the air is going to be taken up by the lattice of the adsorbent, and there will be an instantaneous decrease in the specific humidity levels right at the surface of the adsorbent's projected area. But given that we are talking about sufficient time for the air to regenerate itself, and we are talking about a semi-infinite pool of humid air available for mass transfer, the air regenerates the humidity level from the upstream air, and depending on the temperature and the humidity level of the air, the adsorbent achieves saturation. In order to model the desorption was modeled as a completely temperature-dependent process in order to take away or in order to offset the fact that the pressure swings are going to be created due to the difference in the temperature of the air. When the adsorbent has been saturated by the water molecules, the increase in temperature of the ambient air will cause the RH value at the same specific humidity value to go farther down the psychrometric chart and achieve a localized difference in pressure. That difference in pressure will also be accompanied by an increase in enthalpy due to the increase in the temperature from the adsorption ambient temperature to the desorption ambient temperature, which will then excite the adsorbed molecules by supplying the necessary isostatic heat. And then the excessive water molecules, which are now desorbed species, will become a part of the air. And like the assumption that was made during the adsorption process, that the air is a semi-infinite pool, the water vapors will then disperse themselves, and the overall humidity of the air is not going to be changed, and the adsorbent will be said to be desorbed. Developing on this particular model, we come across at different phenomenon that we need to understand in order to quantify a value of the best possible adsorption and desorption process that can happen. All of the adsorption process, if it follows the simple adsorption model as discussed in the earlier slides, will face changes in 5 different domains. The first thing is the uptake, the second comes the kinetics, the third comes the surface, the fourth comes the ambient, and the fifth comes the desorption. Mostly what has been seen is that when we talk about reporting different and novel materials to extract humidity out of air, we are very focused on the uptake, and some papers also might go towards the kinetic side, where they are going to tell you about the rate constant of the adsorption and desorption. But when we talk about the experience on the field, we have to take a look at the ambient temperatures and try to create a couple between the ambient temperatures and the specific property of the material in vivo, so we can come across a combined efficiency such as we do for our usual mechanical systems. The inspiration was to develop an indicator for for each of these 5 domains, and then the final performance indicator would have been the multiple of these separate indicators, which are going to tell us about the effective process of the adsorption or desorption taking place. When we started with the development of the indicators, the first indicator that was to be developed was on the uptake. The reason that it is one of the most important indicators out of the 5 domains is because the disclosure of the data which is used in this indicator is very common, and for any adsorbent, this is the first variable that we are supposed to see. The uptake indicator, or every indicator that will be discussed in this presentation, are going to represent a ratio. That ratio will be going to be a value that is going to be driven by the changes in the temperature and pressure at field versus a maximum value that can be limited by the ambient or the material. The uptake indicator is basically a ratio of masses, and it depicts the maximum extractable desorbable mass, which means the amount of water that has been desorbed. So it encompasses both the temperature of the desorption and the temperature and pressure of the adsorption process. What it effectively does is it indicates the window of operation. If we see that the value of the gravimetric uptake during adsorption is very high, but we are not able to get enough water out of it, we are actually operating in a very narrow window. Given that the equilibrium adsorption gravimetric uptake is going to be very high compared to the time-dependent gravimetric uptake. Since the motivation was to develop the indicators so they behave as efficiencies, the values had to be modulated between 0 and 1. The uptake indicator modulates that value between 0 and 1 given the specific ambient conditions during adsorption. The second indicator that was developed was on the thermodynamics of the desorption process. We know that if we are to rely on the hot air to completely desorb the previously adsorbent, or in this case MOFs, the difference in the enthalpies of the air is going to supply the necessary amount of energy to excite the molecules which are adsorbed onto the surface. This proportion of the enthalpy inside the humid air is going to be lesser than the heat which is required by the adsorbed molecules at a surface coverage on the equilibrium adsorption state. So still we are at a modulation of 0 and 1 for the thermodynamics indicator XT. What it basically tells us is the window of operation for the energy requirements. The change in the enthalpy of the air will be attributed to the change in the temperature, which is going to be a variable for designing the system, depending on the heaters, or if we talk about renewable energies, depending on what source of renewable energy are we going to use. Given the conditions or the temperature of desorption, we can come across the net window in which the energy transfers have to take place. And how much proportion of that energy is going to suffice for or suffice out of the complete equilibrium adsorption state. The third development of indicator was on the kinetics indicator. The kinetics indicator is dependent upon the surface coverage of the adsorbent layer. Over here, we can see that the denominator is actually an inverse of mass flow rate, or the gravimetric uptake of the adsorbent, where the benchmark is set as 99% saturation. This particular quantity can be modulated to any variable or any degree of saturation of choice, so that the system designers have greater control if they want to achieve a long period of cycles, or if they want to use rapid cycling and achieve a larger output by rapidly cycling the adsorbents. What it does is in a kinetics plot, it is actually going to indicate the closeness to the settle point, because the longer the time it takes after you're very close to the settle point, it is going to be less effective to leave the adsorbent to adsorb, because it has actually went through the major chunk of its adsorption, and now the remaining adsorption is just taking more time compared to the previous adsorption times. In the same way, the desorption indicator for kinetics can also be explained. And over here, the desorption, the benchmark of the desorption is again set to be at 0.99 of the complete adsorption. But this can also be selected as with the adsorption indicator based on the closeness of settle point that we want to achieve. Finally, the development of the structural indicator, or in other words, the indicators that tells us the spread of the particular sample of desiccants, in this case, MOFs. It's a very simple form of stating the level of area that has been projected to the stream of the air, given that there is a maximum BET surface area of that particular adsorbent. And then when you and then in order to get the effective area or the effective proportion of that area, we can then multiply it with the effective proportion of the total pore volume. And this particular variable can be extracted from the lab tests that are being carried out at the time of designing of the materials. The overall indicator then becomes a multiple of each one of those indicators. And since all of those indicators are modulated between a value of 0 and 1, the overall performance indicator, or XPF, is also going to be a value between 0 and 1, which is going to proportionally tell, given a specific condition of ambient temperature and humidity levels, and given that you have set a certain temperature for desorption, what is the effectiveness of your system with a certain desiccant that is going to work for you in the adsorption and desorption cycles. The structural indicator is again going to have a high impact on the magnitude of the value of the total performance indicator, because this indicator is going to be the smallest one owing to the larger surface area of the newer materials and the smaller range of spread that we give to those specific materials. This is a summary of how the indicators are combining the material and machine interfaces. The materials are made in the lab, but they have to be serviced inside a field where they have to prove themselves worthy of the temperature and the relative humidity and the desorption temperature and the time of adsorption and desorption, both that we are going to give to it. So uptake depends upon the temperatures and pressures, which then couples with the isotherm uptakes. Thermodynamics is then going to couple the change in enthalpy of the air between the adsorption and desorption temperatures, which is going to be compared with the isostatic heat of the materials. The surface is then going to compare the material given area for the adsorption of water compared to the spread that we have given the adsorbent, which might be limiting the uptake of the adsorbent due to intercrystalline diffusivities. And similarly, the kinetics is then going to tell us the amount of time, whether it is sufficient for us to work nearing saturation during that time. The last step was to determine the performance indicator and give a proof of concept as various conditions. During the research, there was experimental work done, which is under review. I'm sharing some results from the literature experiments that has been done on the materials. Some of these papers are those papers where newer materials have been disclosed. For example, Anique et al. In 2019 first disclosed the values for above 303, and then Fatih et al. 2018 first disclosed the data for above 801. The reason for taking this approach is to really address the gap that is created between the material scientists and the planning engineers, the systems development engineers. So the laboratory values of the materials of the most purest form of the materials can be transformed into readable values that can be applied practically to the systems. And later on, these indicators can also be used by the smart logic controls of the systems so that they are always striving to achieve a better value of each one of those indicators. So a model was developed on MATLAB and all of the input data was entered. And we can see that the materials, given the temperature and relative humidity values, assumed certain values of the gravimetric equilibrium uptake. And then on the right-hand side, we can see the kinetics plot, where we can see how much saturation has been achieved given the time set by each one of those experiments. We were then able to identify the variables that were going into the specific indicators, and here is a snapshot of how those indicators of how those indicators were made, and how were they giving the values of for each one of those experiments. We can see that for the experiment one, which used MOF 801, the overall indicator was very high, and the reason was attributed to the higher value of the structural indicator excess. And the higher structural indicator excess was due to the fact that in experiment number one, who used MOF 801, the MOFs was pelletized, giving a higher surface area for the MOFs to absorb water. On the other hand, if we try to compare the uptake indicator, which is the most commonly used metric when it comes to choosing a material, each one of the experiments yielded the same values of the uptake, and they revolved around the mean value of all of them combined, which again builds confidence on the fact that relying on the uptake indicator alone is insufficient to come at a conclusion for choosing a good adsorbent for the specific conditions of the field. Similarly, when we talk about the thermodynamics indicator also yielded a somewhat similar value, but the for experiment number 5, which used aluminum fumarate, the values were very high. The overall performance indicator led us to the conclusion that if we were going to plan to make a system for ourselves, and we wanted to serve in field, and we had 5 different locations, then for the specific adsorbent that we are using, the combination of experiment number 1 is going to yield us a greater effectiveness than the other combinations, as in 2, 3, and 4. MOF 801 in the combination of 2 yielded the worst performance factor value, and the reason is that we can see that in experiment number 2, the time given for the adsorption was way beyond the time it actually required to achieve equilibrium state. Coming on to the conclusion is that atmospheric water harvesting are a very unconventional source of water, but they become highly exploitable during the time of emergencies, which is a point of interest for the global South economies. Passive atmospheric water harvesting are becoming more popular, as also indicated by the presenters earlier. There is a lack of comprehensive material plus machine indicators for system development, as was discussed in the keynote of this session. A great deal of research is being carried out on the next generation of the adsorbents, and MOFs are definitely an avenue. What this research was able to contribute is the development of indicators in a 3-step process, which yielded a set of 4 indicators, which attempted to completely define the performance of a system in 5 different unique domains. The future recommendations which might result from this research, or the research that stems on the metrics using the atmospheric water harvesting devices, is the synthesis of novel materials can be disclosed for their system behavior, given certain examples or certain cases studies for different regions. The model, which is a very simplified model and a cyclometrically driven model, can be further enhanced by incorporating additional cooling and heating and for high velocities, and then the effect can be studied for the mass transfer balance that is going to happen between the velocities of the air and the mass transfer of the water from the air into the lattice. And then the identification of maximum practical values of the structural indicator can be set by pelletization, and the strategies for pelletization has to be without amorphization, so that we do not destroy the properties of the crystals to adsorb water molecules, but we are still giving them a big value of XS. And finally, we can study MOFs in the future with multiple selectivities for the simultaneous absorption of greenhouse gas emissions and the water vapors. These are some of the references that has been used in order to come across the various findings in the research. And I will now end my presentation here. Thank you for being a patient listener.
Thank you. Awesome. If there is any question, please just raise your hand. I will unmute you, or you can just write down in chat or QA. Right now, Costa asks you to put the DOI of your paper.
Sure, I will put it in the chat.
Okay, perfect. Simon mentioned, I think that the long-term stability of the absorbent should also be considered as a key performance indicator, particularly given the well-documented water instability observed in some months.
Yes, just to respond and reflect on Simon's comment, there is one research paper that is under review. As soon as it gets out, I'll be more than happy to share with the association, which can then disseminate it. And it depends on the optimization of the systems based on these indicators for multiple cycles.
Okay. Mr. March asks for commercial validity, cost, gram, and ability to source the desiccant are factors as well.
Yeah, the cost per gram and the availability of the desiccants, specifically MOF, are a big challenge. And before we even tend to buy specific desiccants for our application, we really have to give to get a holistic perspective of the systems that we are going to make. So this is a step before we are actually trying to procure the material and trying to understand, shall we buy material A or material B, given the cost, or whether the cost that we are investing in that material is going to be fruitful for us or not in the longer term.
Thank you. Thank you. I really appreciate it. Before going for our next speaker, I would like to share one point with you. Okay. I think right now you can see my screen. Actually, we are looking for some volunteers because we want to have the global testbed. In this case, we want to connect multiple atmospheric water harvesting system to air quality sensor and monitor water quality as well. This means we want to collect data about effects of air quality on harvested water quality. Just please scan this QR code and join us. We want to put devices in multiple locations around the world to monitor air quality and water quality. I will also put the address in the chat. Thank you.